Okay. So we're going to go ahead and start by looking at focusing a lot more on resonance. I, again, cannot overemphasize the importance of resonance. I know I'm going to say that about a million topics, but really, really about resonance. It is so important for understanding organic chemistry and the stability of various compounds. One of the ways to learn about resonance, this isn't how I did it as a student, but your book has this kind of novel way of doing it. It works, I think, is to notice certain patterns that we will find in resonance. So we can break this down into a few different kind of categories so that we know when resonance will occur and how to handle it. I think this approach might get a little memorization heavy, but I think it also helps students to see it. So the first pattern is going to refer to vinylic and allylic positions. So these are words that we see a lot. Don't worry whether something says vinyl or vinylic or allyl or allylic. Those are going to mean essentially the same. Okay. It's just noun versus adjective. Okay. So vinyl and allyl are going to correspond to positions on a carbon-carbon double bond. Okay. If something is bonded directly to a carbon-carbon double bond, then that is considered to be a vinylic position. Anything bonded to something which is bonded to the carbon-carbon double bond is considered allylic. So if we were to go ahead and take a look here at some examples. There we go. I think this might be confusing because the things that are actually vinyl are not the highlighted groups, but what's bonded to the highlighted groups. So anything that's here, 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 or here is vinylic. Anything that's bonded to those is allylic. So if we were talking about whether something is vinylic or allylic, we just look in reference to what it's bonded to. So this chlorine is bonded to a carbon-carbon double bond, right? Anything bonded to a carbon-carbon double bond is vinylic. How many other vinylics are there in this molecule? Chlorines.
One more.
One more, and counting left to right, it is the
left one.
Second one. Second.
Oh, second one. Sorry.
Yeah, that's vinylic as well. Allylic is bonded to the carbon that is vinylic. So if we look here, this carbon right here is vinylic, right? The one I just colored in blue. Because it's bonded to a double bond, okay? So this chlorine here would be allylic. Actually, no, it doesn't work that way, sorry, for carbons. That's why it's kind of confusing. These carbons are the vinylic ones. Anything bonded to those groups that are there would be considered allylic. So this chlorine would be considered allylic. This chlorine would be considered doubly allylic. Doubly so because if we look here, these are vinyl carbons. Anything bonded to a vinyl carbon is vinyl. This is an allyl carbon. Anything bonded to a allyl carbon is itself considered allylic. Okay. And so this chlorine here would be considered neither. Okay. So let's take a look at some examples here that we could get. So the first one that we would get, this is considered allylic. It is on a carbon next door to the double bond. Okay. Carbon next door to the double bond, allylic. So whenever we have that, the lone pair can be donated towards the pi bond. And this is the pattern. Double bond goes towards the bond to make a new bond. And then this pair goes here. You have to move that pair, the pi bond pair, because otherwise this carbon would have five bonds, right? You can't have five bonds. So it might help to draw in the hydrogens in these kinds of scenarios, okay? And so the resonance contributor would look like this. We now have a lone pair on that side and a negative charge. I probably could have drawn that a little bit bigger. These two are equivalent resonance structures because if you flip one over, it looks exactly like the one you started with, correct? Good. This oxygen is in an allylic position, okay? I don't think I would want to call it an allylic oxygen, but it is adjacent to a double bond here, and its lone pairs can therefore follow the same pattern. They can be pushed, and that's the word we use, pushed. They are pushed to form a new bond here. In case there's any lack of clarity here, let me draw in the hydrogens. Right, that carbon has two hydrogens on it, for a total of 4 bonds. And then these electrons, because now you would have 5 bonds on this carbon, so you can't allow that, so you can push these electrons onto this carbon. But now the oxygen has a double bond. And there's still one lone pair left over. I'll draw in those hydrogens. Or you could have just written CH2 if you'd wanted. What else do I need here?
Lone pairs on the carbon.
Good. This double bond, the pi bond, became a lone pair. Which is negatively charged. What else do I need for this to be finished?
Would you need a positive charge on the oxygen?
Very good. I need a positive charge on the oxygen. And that's why, again, you need to get really good at recognizing those patterns. Good. So we have a positive charge on that oxygen. Any questions about that one? No? Okay, can you try the other three? The arrows. So it's going to be 2 arrows on each of these. So I'll give you about a minute to do that. All right, so let's go ahead and take a look at those arrows. And you will notice that you see it's the same general pattern here. We have a lone pair electron going towards a sp2 carbon. That's probably another way to look at it. sp or sp2. We're mostly going to be interested in sp2, but sp would be fine as well. So anything other than an sp3. So these lone pairs are moving towards there, and then these electrons get delocalized. Notice how I like to draw the arrow above the atom. That's not a requirement. You could draw it directly at the atom. I just don't like to draw it right at a lone pair. It just makes me feel uncomfortable. Electrons should never really point towards other electrons, right? Same idea here. These lone pair electrons are going to make a pi bond, and then these pi electrons will go to the nitrogen. And then same there as far as here. Okay, so if we looked here, that would give us an oxygen down here. Oxygen used to have 2 lone pairs, now it has 3. What else do we need? A double bond, good. And formal charges, the oxygen on top needs a
minus.
Good, a very good negative partial, and the oxygen on bottom.
Less.
Yep, very good. So you'll notice the negative always pretty much ends where the arrows are going towards, right? In the first one, the electrons are going right to left. In this one, they're going from top down. So the negative is moving that way. Same thing here, that here the negative is moving up. The arrows are pointing towards the up. Same with all these three, the electrons are moving up. So let's see on this next one here. I don't really like doing this. I'm going to rewrite this as CH3. Okay. That means the same thing, right? Should mean exactly the same thing. I'm just clarifying that that's a CH3 right there. And you agree this is not a functional group you've seen. Double bond nitrogen. Okay. We won't see that until next semester. That's called an imine, Okay, so what has changed here? The nitrogen now has 2 lone pairs. So what formal charge would this be here? Should be negative. And then what else needs to be there? The lone pair on the bottom became a
A double bond.
A double bond. Good. And although it's not shown, do you all see where I'm pointing the lone pair right here? That has how many hydrogens on it? That carbon has
2.
one. Okay, because you'll notice down here, 3 bonds, this would have been 1 hydrogen. Okay, if there was 2 hydrogens, then you couldn't have also a lone pair. That would be 10 electrons. You'd be exceeding the octet rule. Okay. I know it's not obvious when you're first doing this, but it gets to be so after a while. Okay, and then the final one. Taking a little longer than I'd wanted to here. Okay, so new double bond between the nitrogen and that 1 carbon. We lost a double bond. So this is now has 3 lone pairs. And my formal charges, the oxygen is
-1.
-1, and the nitrogen is
+1.
yeah. You should virtually never have anything other than -1 or +1 on anything in any of the common organic atoms. Sulfur, it's rare to see -2, but you will occasionally. Okay, so we all okay with those? And in all cases, the electrons are delocalized over 3 atoms. Do we see that? We have 3 atoms total here. What kind of atom was in the middle? The hybridization of the atom in the middle in all cases was
Carbon.
the hybridization.
Oh, sp3.
2
It's 2. Oh.
in the middle. That meant there was a p orbital here, right? Okay, so these electrons are kind of going into that p orbital to make a new pi bond. Okay. So dealing with the allylic positive charges here, okay. Only 1 curve is needed. That doesn't look right. That doesn't look like it belongs here. Okay. I also did not make a note of this, but I don't think that was on the slide. But let me just be very clear about this. So when we're talking about lone pairs, allylic lone pairs, that means, again, they are adjacent to a double bonded carbon. So the electrons down here we saw could be delocalized to this carbon right here. I mean, you push them here, and then these electrons get pushed here. You cannot do that with these electrons. Why can't you push any of these electrons to make a double bond? Not on the top one. What would end up happening if you pushed these electrons next door? This carbon has what? Hold on, let me finish that question real quick. This carbon right here has how many hydrogens on it?
3.
3. So if you push these electrons here, that carbon would be making 5 bonds, right? So you can't do that. You can never push towards an sp3 in resonance. sp3, all the rooms are full. This is sp3. There's 2 hydrogens on it. If you try to push those electrons to make a new bond here, that carbon would have 5 bonds. It would be exceeding the octet rule. So never push towards an sp3 in resonance. In a reaction, that can happen if a group is going to break away, okay? But groups can't break away in resonance. Remember, the rule for resonance was no you know, the atoms have to stay connected. You can't change the connection of atoms. Okay. Good. All right, so we already did this, so we're fine there. So dealing with allylics with positive charge. So we already saw that you only needed one curved arrow when there were negatives. We already did this example, right? What if there's a positive charge on the allylics? Electrons would love to go towards that positive charge, right? Remember, negative goes to positive. So we can do the same thing here with an allylic cation. That's what we would call that here. And so down here, same idea. These electrons can go towards the positive bond. So let's take a look at that. Again, I don't really know why I have this here. I should have gotten, I don't know why I drew that. I think I copied and pasted the wrong thing. All right. So what I meant was this. I meant I think this is what I meant. I meant this. And this would be able to go to where? Real quick, how many hydrogens on each of these carbons? On the carbons at the ends, how many hydrogens are there?
3.
2.
Oh, because of the double bond and positive.
Yeah, exactly. If this is double bond, then that's the CH2. Okay.
Mm-hmm.
You know, and it might be easier when we write it up here too. It might be easier when you're first learning it to do it this way. Okay. So the electrons will go there. And again, I'm not done. Because if we started with a positive charge, there has to be a positive charge somewhere. And it would be right there. Yeah, I think your book is a little strange in that it takes the tactic of getting you started right on these bond structures. And it's, I think, still very important that you see the hydrogens when you're first learning about resonance. Okay. Because that's the only way you can make sure you're never exceeding the octet rule. All right, so CH2, CH, that's what we have there.
Professor?
Yeah.
So there's a CH2 on the left side, right? Because of that plus, right?
Yes,
Because
okay. Carbon is making 3 bonds, right? 2 hydrogens and to this carbon right here.
I see.
So
4 minus 3 is that plus. All right.
Plus 1. Exactly. The resonance hybrid would look like what? The lone pairs can be, I mean, the electrons are delocalized. And where are the positive charges turn into partial positives, if that makes sense. Okay. That's important because it tells you that if something with electrons wants to come and react, where are they going to attack? The carbons on the ends or the carbon in the middle? And we call that an attack. If something wants to give its electrons, are they going to give it to The carbons on the ends or the carbon in the middle would be your guess.
On the ends.
On the ends, because the ends are the positives, right?
Mhm.
Okay. Could you tell the difference, by the way, on either of these in reality? You couldn't, because this one is exactly the same as this one flipped upside down, right? Or flipped left to right. Okay, let's do the one I had on my notes, which for some reason disappeared here. I don't want you that big. Let's see here. There we go. Okay, so same general idea here. 1, 2, 3. Not beautiful, but it'll do. Okay, so let's take a look at what we can do. So where do the electrons want to go?
Toward the positive.
Yeah, towards the positive. So these electrons could go right here. And remember, what's at the end right there? That's a CH2, right? It's just a longer version of this molecule that we just did here. Good. And so let's just do that. That's one arrow. So we would now have a double bond here. The carbon had 3 bonds before, right? It had 2 hydrogens. That carbon now has 4 bonds, so it is neutral. Did anything change to this double bond over here? Nope. And what else do I need to put in that's missing?
The positive side.
Yeah. And if we want to draw in the hydrogen, there's a hydrogen here, right? So this carbon had 4 bonds. Now it has only 3. So it's a positive. But we're not done. Number 1, I could draw the electrons going back, but that would just take us backwards, correct? So if I drew this, and I'm going to get rid of it in a second, that would just take us back to the first one. So that's no new resonance structures, so I won't count that for right now. But you agree that I now have another allylic carbocation, and that these electrons could come here. And so now the pattern is double bond, double bond. And where's the positive charge now?
The 5th carbon.
Good. Exactly. It's on the 5th one from the left. And again, to really do this well, you have to see the hydrogens. And that's why sometimes it's easier to start by writing them as condensed structures. Lewis structures usually just take too much time. Okay, so a hybrid. Where can the electrons be? If we combine all the hybrids, where are pi bonds? There's a pi bond between the first and the second one. Here there's one between the third and the fourth, second and the third. Here's one between the third and the fourth. They can get everywhere except the last one, right? The last bond is the only one which never has a pi bond. So I could draw a hybrid like this. Most people don't curve them like that, but okay. And where are the partial positives? Counting from the left, wherever there was a positive. So this would be the first one, the third one, and the fifth one. So what we will find on later is if I were to add hydroxide, and don't draw this right now, hydroxide with its negative charge could, in theory, attack and try to make a bond here, or here, or here. Wherever there is a positive charge, we might expect that to happen. Okay. It gets more complicated than that, but it's good for giving you an idea as to where things like to react. So right there is the positives. By the way, there is a term for this. That we refer to a lot. Okay. Whenever we have an alternating pattern like this, we would say that this is conjugation, okay? Or conjugated. It is an alternating pattern of double and single bonds, right? Although I'm going to use the word pi bonds because technically one of those could be a triple bond too. Okay. I could make one of them a triple bond and I would still use the word conjugated. All the carbons are I'm going to get rid of this last one so that it's totally clear. Okay. All the carbons are what hybridization here?
SP2.
SP2, good. So they're all SP2. I don't want that in parentheses. SP occurs sometimes is seen too. The key thing about this is SP2 or SP has lone p orbitals. They have p orbitals. It can't be SP3 because SP3, all the p orbitals are hybrids, right? That was the idea. So long as you have p orbitals that are all lined up here, you can do that. And if I asked you for a resonance hybrid, we would see that the electrons can be delocalized over all of this. So that's what's called conjugation. Any alternating pattern of single bond, double bond, single bond, double bond, or single bond, double, single, triple. Okay. The key is that you have a single separating pi bonds. Okay. So that's an easy pattern to see, right? Double, single, double, single, double, single. You see that in a lot of chemicals. Let's look at a very common example. Here's a chemical you should know. Beta-carotene. You've heard of beta-carotene, I'm sure, right? Beta-carotene is in carrots. This molecule is very conjugated. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond. Okay. Here's another one. Lycopene. Again, very, very conjugated. Not 100% though, because you see right here, you see where I'm pointing right now? That's SP what right there? These two right here are SP 3. So that means you can't move the double bond there. But all of these ones are double, single, double, single, double, single, double, single. So you could move the electrons across all of those up until you get to these sp3s here. Incidentally, what is true about both lycopene? Most organic compounds are white. Lycopene is not. Neither is beta-carotene. Neither is a lot of other compounds that are conjugated like this. Let's look at a dye. Here's tartrazine. Tartrazine, very conjugated, double bonds, single bonds in the benzene rings, single bond, double bond, single bond, double bond. You see that right there? There's a lone pair on this nitrogen, which means we can do resonance. It's an allylic lone pair. So all the electrons on this molecule can be pushed all over the place. What does that tend to mean about all of these compounds? This is a dye. All of those compounds are colored, okay? So that's going to have a very important effect on color, as we find out later. They can all absorb visible light, which means they will not be white, but they will appear colored. Okay, so there will be a whole chapter about this, probably the first chapter of next semester. Okay. I want to go backwards in my notes to one thing that I forgot to mention, and it just reminds me right now. Can we go back in your notes, please, to why did I close that? Extra credit quiz. I think it was this. No, I don't have it. Okay. Go back in your notes to where we were doing functional groups. Aromatics, remember aromatic? We never say an aromatic is an alkene. Okay. So if I asked you the functional group right here, you would say aromatic. You would not say aromatic, alkene, alkene, alkene. Okay. So I just want to make sure about that. Is this conjugated? Yes. Double bond, single bond, double bond, single bond. But it is not an alkene. So please never use the word alkene in a benzene ring here. Okay. By the way, are you ever allowed to just leave the double bonds off? No.
No.
Yeah, and that was in my notes about the lab report, because I see that all the time on lab reports. Never leave them off. If you want to be lazy, draw a circle in the middle, but never just completely leave them off. Because like here, I would be confused. If you know, this tells me there is no double bond. So be please, 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 same thing here. This means no double bonds. This is not aromatic. So whenever you see a six-membered ring, don't call it aromatic. It has to be double, single, double, single, double, single, and then it's an aromatic. That's the only way it's aromatic. Okay, so be very, very careful about that. Sorry, I just realized, you know, I didn't say that the other day, and I think I've got, and maybe I did and I just forgot. But I got into a panic when I thought, oh no, when I gave the new problem set out, I'm going to have all these people leaving out, you know, or calling all the benzene rings aromatic, you know, alkenes. Don't call benzene rings alkenes. Different reactions entirely. Okay. The next pattern. God, I'm spending way too much time on this. But that's good because I didn't have much planned for lab anyway today. So, except watching a video and talking. All right, so lone pairs next to a positive charge. This should be a no-brainer. Electrons love positive charges. They're going to go right to it. They don't jump over the bond. This is something you should be noticing. Lone pairs can only become bonds, and bonds can only become other bonds or lone pairs. They can only be pushed next door. They don't jump. Okay. So this is a very common pattern as far as this goes. This one is very important because we're going from a carbon with no octet to a carbon with an octet. The structure on the right is much more stable. What is the name of this compound? Does anyone remember? It's an important solvent.
Ketone.
That's the functional group, ketone, but it's a solvent. It has "-one" in its name because it's a ketone. Anyone remember? Acetone. It was one of the solvents we talked about. Okay. And notice this one, the lone pair is moving towards the positive charge. Now everything has an octet, but you still have a positive charge. Okay. Nitro groups are particularly common when we're dealing with functional groups here, or when we're dealing with resonance. I don't want to call a nitro group a functional group per se. It wasn't on the list. Okay. But nitro groups, usually abbreviated NO2. Okay. Will generally have a positive and a negative adjacent to each other, like this. Very, very common functional group. So what would this look like if I wanted to move this? This would be, do the electrons want to go from right to left or left to right? Negative wants to go towards positive.
Left.
It'll go right to left. But there would be a problem there. Why is that a problem? Nitrogen.
Octet.
Yeah, but can I fix that? I can.
Yes.
Take the double bond and push the electrons to the oxygen. Okay. So if we look at that, that would leave us with a nitrogen here. On the left side, the double bond has become a single bond. On the right side, we now have a double bond. 3 lone pairs are now 2. And formal charges?
Minus
The-
on the
Yeah, minus on this oxygen and positive on this nitrogen. They are equivalent, right? Because if you flipped it over on its side, it would look exactly the same. But don't say there's only one resonance. These are 2 separate resonance structures. They just happen to be equivalent.
Why can't the electrons move to the carbon on the bottom?
Because it's CH3. If you moved it to the bottom, the carbon has an octet, right? And that would give you an
All right.
octet. You can only move towards an atom with an octet if it can do what? Let go of a
Electron.
let go of, yeah, a pi bond usually. Okay. Sometimes you'll see electron pairs there, but usually it's a pi bond. So usually if you go from a lone pair to make a new pi bond, this has to let go of electrons to move to the next atom.
So if the CH3 was connected to another CH3, so it was like a CH2 connected to CH3, would that be possible?
That would not work because CH2 would still have an octet, right?
Okay.
If the way you're describing it, because if you have CH2, all you're changing is one of the hydrogens to a carbon, so it still has an octet. Okay. What would be the only way that could happen? instead of CH3, it would have to be CH2,
CH2 minus
CH2 plus.
plus.
Then you could push the electrons toward it. Okay. This would be a horrible, makes me ill to even look at. Positive charges next to each other, very, very bad. Don't ever do that. Okay. If it did have a lone pair, then that could move towards the nitrogen too. Okay. But I'm starting to, the issue is I'm also drawing molecules that don't really exist here. All right, so this was CH3. CH3. Good. This is called nitromethane. Okay. Pi bond between atoms of different electronegativity. Where the electrons are going to want to go. Where do they want to go? This isn't a new pattern. This is a pattern we've already seen. If you're going to pull them anywhere, given the choice, do you want to push these electrons to the carbon or the oxygen?
The oxygen.
Yeah, the more electronegative. Exactly. So going the other way, would give you this. And this is bad for a wide range of reasons. It's not impossible, but it's just bad. It's very bad because it's better to put the electrons on the lone pair on the more electronegative atom. En will always be my abbreviation for electronegative. And either way, what's the problem with either of these resonance structures? What are they both? What's wrong with both of them? Not wrong, but what makes them both a little bit not as good as the original structure? You're lacking an octet, right? You don't have an octet on carbon here, and here you don't have an octet on oxygen. Okay. I'm not saying it's not possible, but I'm saying it's not important. It's an irrelevant structure. So it's the same thing here. You could push these electrons to the carbon, but nitrogen is more electronegative. So if I said you only get to do one or the other, you should go towards the nitrogen. That would be a much more reasonable choice. Although even that is not a great resonance structure when we start going over them. The reason, as we see, is all of a sudden you've added charges. You didn't need charge. You could have just left it alone. So when we go to talking about which is better resonance structures, the one on the left is far better than the one on the right, which would be much, much, much better than trying to push the electrons onto the carbon. So there's going to be a bunch of guidelines that we come to on how important is a resonance structure and how important is it not. Pi bonds in a ring. Benzene is an incredibly important molecule because it's not unique, but for having 6 carbons, for a number of reasons, it's particularly stable because these lone pairs can move in a pattern here. Benzene could be drawn either way, and it would be considered the same thing. And these are considered resonance structures. The 2 different ways of drawing benzene right there are considered 2 different resonance structures. And remember, more resonance means generally more stability. It stabilizes the molecule here. Okay, so that's also a very common pattern. And this kind of issue comes up in the problem set too. All right, so if we were to quickly see a summary of all these. So figure 2.6 summarizes the most common patterns that we see. Nowhere do you see a lone pair attacking another lone pair, right? That would make no sense. Lone pairs want to move towards something that's positive, or they want to move towards an atom which can hold it. Again, this isn't really going to the lone pair, it's going towards the oxygen. Okay. So using guidelines here, let's look at lots of different things that we can do here for this molecule. Let's see what we can do. You know, and actually, I'm going to put that off first. Well, no, let's do it. I don't know that I want to do all of them though, because it could take a long time. Okay. From this nitrogen on the top, what could I do? I could take that lone pair and move it towards the
Right.
Yeah, towards the right. Good. I'm just gonna do these all by hand, so my rings might look a little bit messy. It's much easier to do this on paper. Sorry, I forgot my arrow. Arrows do not need to be blue. I'm just doing it for right now. That way. It's a little better. Any changes in charge? There has to be a change in charge because the whole thing is neutral, right? Positive, negative. If there's a negative here, then where's the positive now? On
Nitrogen.
the nitrogen on top, right? Good. I really can't do anything with this lone pair down here. Why can't I push it up to this carbon right here?
The octet becomes not an octet.
Yeah, it would exceed the octet rule. Pushing these electrons to this carbon would make no sense because then it would be a negative charge where you don't need one. It's not to say it's totally wrong, but it wouldn't really make much sense. So I'm going to ignore pushing these two electrons onto this carbon. I'm not going to do this. Okay. That really would not be a good pattern. Can I push it next door towards this carbon? Can I do this?
No,
Why not?
the octet is exceeded again.
Exactly. It would exceed the octet rule again. There's 2 hydrogens on this carbon. You don't want to ever push towards a carbon with an octet unless it's got a pi bond it can let go of. Okay, so that's not going to work. All right, let's take a look over here. How about this oxygen? I could push these electrons down here. And then I could push now that would exceed the octet rule, right? So I can't stop. I have to take that pi bond and push it somewhere. For right now, let me just push it onto that carbon. This is pattern number 1 that we talked about, right? Pattern number 1, which was you push the electrons here to make a new pi bond, and then the pi bond becomes a lone pair. So that's an acceptable choice.
Professor?
Yeah.
How'd you know to push that double bond down and not up?
What do you mean by down and not up?
All right, so you know how you pushed it
Instead of like this,
yeah, so exactly.
it's exactly the same thing.
Oh, same thing? Okay, so you can do either way.
Either way would be fine. Whether it's above or below doesn't make a difference, unless it makes it messier. Okay. So now the oxygen is double bonded, right? Because these electrons went here, and these two electrons went where? Onto the carbon. So I need a lone pair. So that's going to be negative right there. And I could do this then. Let's go. The only way these electron pairs could go is up, right? But now this nitrogen would have, this carbon has an octet. So let's push those electrons to the nitrogen. And that gives the nitrogen its lone pair back. Yuck. So this one's a little hard to draw. 7-membered rings are always a pain to draw. Yuck. All right, so some of the bonds got really big and squiggly. Sorry about that. Oh, I know why there's a problem. Forgot a carbon. There we go. Good. You know what? I'm just going to start that one over. It just doesn't want to go. All right, so let me do it this way. 7-membered ring. 1, 2, 3. No, this won't work.
Drawing this feels wrong.
Huh? Yeah.
Drawing this feels wrong.
No, I mean, this is a totally normal case. It's just really hard to do without nice software to draw the 7-membered rings the way we want, because drawing 7-membered rings just feels unnatural. I can't believe I'm having such a hard time with this. It's just, as I said, not doing this on paper makes everything seem screwy. 1, 2, 3, 4, 5, 6, 7. There we go. Okay, it's a little tilted, but I think it gives us what we need. There we go. Okay. And the nitrogen would be, oops,
Shouldn't the double bond be on the?
double bond
Okay.
should be the other place, yeah. There we go. All right. Good. And we need a lone pair on nitrogen. And we need one there. Good. Now, what is unique about the one on the right compared to the others? It's also the only one with
No formal charge.
no formal charges, right? Good. And let me put those lone pairs on oxygen. All right, so those are several cases that we have right there. Okay, I don't want that. I want PowerPoint. Okay, so there we go. The last thing I want to deal with here is comparing the resonance structures and seeing how important they are. So we already talked about, like nectarines as an analogy for resonance. A nectarine is not a peach, it's not a plum. What is it more? I don't know, to me a nectarine always seemed more peach, but I could be wrong. I guess you could deal with it here. What if you made something that was 65% peach, 34% plum, and 1% kiwi? Would it be really green and hairy? Probably not, because kiwis are only 1%. It's probably going to be more yellow-orangish, not quite as hairy as a kiwi, maybe with a little bit of purple tint to it. But you get the idea, is you're mixing things here. And so what we have to deal with here is the same scenario. I've got 4 resonance structures here, and they aren't all equally good resonance structures. Some are more important in describing the molecule than others. Okay. So the resonance hybrid looks most like the most stable one. In other words, where the positive partials are, where the electrons are delocalized, all of those things. So we have to have rules here in terms of what things give us better resonance structures. So formal charges, the more formal charges you have, the less stable. Especially when you have a positive one on an electronegative or a negative one on a low electronegative atom. So for example, having an oxygen with a negative charge is a much better option than a carbon with a negative charge. Okay. Having nitrogen with a positive 1 charge is much better than oxygen with a positive 1 charge. Complete octets make molecules much more stable. So let's go ahead and draw 3 resonance contributors for acetic acid. So acetic acid is CH3, COOH. OOH, this notation is common for a carboxylic acid, or CO2H. Okay, I'm going to draw it without bond lines. I'm going to do it the old-fashioned way here. Okay, so some ideas. Where could I push the electrons? How about from the double bond? Can I push them towards the oxygen on the bottom? Can I do that? Yeah, I can't do this because that oxygen would exceed the octet rule, right? And there's nothing it can let go of. But I can do this. Correct? What else can I do? I can move the lone pairs from here to there. Okay, now in terms of importance, if I'm going to rank the general importance here, I would say this. Number one, so in terms of importance, the best resonance structures give all atoms octets. That should be your first rule. Do any of these structures not have complete octets on their atoms?
The middle?
What's that? Yeah, the middle one. All the other ones, all the atoms have complete octets. Okay. So this is the least important, or the least contributing. Because no octet on carbon. Rule 2 is the formal charge rule. The best resonance structures have the least formal charges. So it's better to have no formal charge at all. So we can now compare the two on there, right? Okay. This one is the best because it has All atoms have octets. And there are no formal charges. Or instead of best, I could say what? The most contributing. In other words, remember when we were talking about our example here of 65% peach, 34% plum, 1% kiwi, this would be the peach part, so to speak. All right, this is the most important one. This is the least important one. So the hybrid is going to look more like which one than any of the others, theoretically. More like the one on the left. Okay, the next rules. That they're not going to be really important here. But going back to what we have here, let's see, best resonance structures. We should avoid putting like charges on adjacent atoms. So for example, this is very bad. No good resonance structure should ever do that. Okay? Put positives next to positives. So if you are going to have formal charges, don't ever put positives next to positives. Positives next to negatives are much more acceptable. Okay. Lower values of formal charge are better than higher values. So in other words, and also specifically, never put you should only have +1 or -1 on group 2 atoms. Sorry, group period 2. On period 2 atoms. Period 2, of course, meaning, you know, boron, carbon, nitrogen, oxygen, fluorine, anything in the second row of the periodic table. And the reason I go through this is for all of those rules, the least important rule is it's better to put negative formal charges on atoms with high on electronegative atoms, on more electronegative atoms. So the whole point, as I said here, is because that statement, I think a lot of people overemphasize the importance of it. It would be better to put a positive charge on carbon than on oxygen. But why is, going back to this example here, here the positive charge is on oxygen, but here it's on carbon. Yes, it's better for a positive charge to be on carbon, but what's much more important still? It's much more important that all atoms have octets. Okay, so this is a better structure. Excuse me, this one on the right is better than this one, even though it's got a positive charge on the oxygen, because every atom has an octet. That is the most important thing. Much better that atoms have octets. So this is the least important consideration of all the others. So if I go back here, which is the most important contributor? If I was to number these, if I was to letter these A, B, C, D. Or it might be easier to find the least important. Probably easiest to find the least important. Least important would be the one with where atoms don't have octets. There's only one of these where an atom is an octet. What's that?
Is that C?
No, every atom has
A, right?
C. It's A.
Mhm.
Yeah. No octet right here. So A is definitely the least important. What is the most important? Going to rule 2. Since all the other atoms all have octets, the next rule is find the ones with the least formal charges. D. So D is the most important, or most contributing. I would project A to be the least. So I'll give this number 1. I'll give this number 4. What would be the second best, second most important, B or C? All the other rules don't matter until rule 5. Rule 5 basically says you should put negative charges on the more electronegative atoms and positive on the less electronegative, given the choice. So what's better, a negative charge on oxygen or a negative charge on carbon?
Negative on oxygen.
Oxygen.
Negative on oxygen would be better. And then that'd be a 3. And sometimes you can come up with ties, you know. It's not always going to be possible to rank all of them. But I would say number 1 is the most contributing, 2 is the next most important, 3 is here, okay? And then this is not very contributing because it's very easy just to move those lone pairs right down there. Okay. So these are important rules. I hope everybody got them. Okay, let's do a few more. God, I was hoping to get halfway through chapter 3 today. So much for that. So I will finish chapter 2, even if I have to do it in the lab. And I will get you memorizing some things over the weekend that you're going to need to start memorizing. Okay. Draw the 3 resonance contributors for the acetate. Acetate is CH3COO minus. So that would be CO, CH3, O, O, O. If I was to add a rule even above number 1, well, I'll get to that in a second. I want 3 total. So if I want 3 total, I'll do the exact same thing as I did last time. I'll move those electrons up. And sorry, I don't really like to draw my circles around the charges. I know the book does, but again, they're optional. And then what could I do also? Move the,
lone pairs on oxygen to make a double bond.
yeah. Okay. I think it's easiest to find the least important. So what's the least important here?
The middle one.
Or least contributing. So yeah, I'll say least important, even though I mean contributing. Okay. Why?
Carbon's octet is non-octet.
Yeah. Not all atoms have octets. Good. And then on top of that, you've got all these extra charges, right? You got 3 atoms with charges. So there's a lot of things going against it. What about these two?
Tie.
They're a tie. They are equivalent, right?
Mhm.
That's another, I would say that's an even bigger rule. If you can get equivalent ones, that's even more important. That's really stabilizing. If you can get 2 really good and equivalent ones, that's super stabilizing. So I would say these two are, they are equivalent and they are by far the most important. All right, so that gives you some good ideas as far as that goes. Let's see. I'll let you, oh, and the resonance hybrid on this, I didn't draw one for the other one. The resonance hybrid would look like this. So wherever there's always at least a single bond, right? There's always at least 2 lone pairs. The only thing that varies is where there's a pi bond. So I would say partial negative, and even though the least important one it's less important, I would still say that's partial positive. So if I drew this molecule, remember how we can color code that with the potential surface? The oxygen ends should appear red. The carbon should appear fairly blue. So fairly negative right here.